Hi, this is Mr. Manley. This is a video on graphing a rational function that has a slant asymptote. As with graphing any function, we want to start off with a table of values. And we're going to, of course, find the y-intercept when x is 0 and the x-intercept when y is 0. Here I can see if I plug in a 0 for x, those zero out, and I'm left with -4 over -2, so that would be a y-intercept of 2. And if I plug in a 0 for f of x, that's f of x is equal to 0, and I'm going to have 3x squared minus 4 over x minus 2 is equal to 0. Hopefully that you know that really all we're interested in here is what will make the numerator 0. Any value that will make the numerator 0 will give us an x-intercept, as long as we don't make the denominator 0 too, in which case we'd have an undefined value. But that's not going to happen here. So we're just going to solve for the numerator really being 0, and that'll be x squared is equal to 4 over 3. So x is equal to plus or minus 2 over rad 3. We don't need to rationalize the denominator. We'll just say we've got plus or minus 2 over rad 3. Then the next thing that we do with a rational function is look for the horizontal and vertical asymptotes. So the horizontal asymptote, well, actually, let's start with the vertical asymptote. The vertical asymptote is found in the denominator. So in that case, it's when is x minus 2 equal to 0. So x equals 2 will give us a vertical asymptote. Next, we look for the horizontal asymptote, and we're comparing the degree of the numerator to the degree of the denominator, right? And what we should know is if the degree of the numerator is less than the degree of the denominator, there's a horizontal asymptote at y equals 0. If the degree of the numerator is equal to the degree of the denominator, there's a horizontal asymptote at a fraction of the leading coefficient over the leading coefficient. And we don't have either of these cases here. What we have here is the degree of the numerator is greater than the degree of the denominator, and it's by a unit of 1. And that's important, that it has to be greater than the degree by 1 unit. So what that is going to get us is a slant asymptote. So we're not looking for a horizontal asymptote, we're looking for a slant asymptote. And we find the slant asymptote by dividing the numerator by the denominator. So I'm going to divide 3x squared minus 4. Now actually I'm going to go ahead and do this with synthetic division, since I have x minus 2 and it's convenient to do that. So I'm going to go a 2 in the box, and then there's 3x squared, 0x minus 4. I'm going to bring down the 3. 2 times 3 is 6. Add 0 plus 6. 2 times 6 is 12. The remainder doesn't really matter here. I'm not going to use it. Go ahead and finish it. So what I have is this is the quotient, right? And that is 3x plus 6. So that is the slant asymptote. So the slant asymptote is the quotient that I get when I do the division if the degree of the numerator is higher than the degree of the denominator, in particular by 1 unit. So this is the slant asymptote. Okay, let's take a look at graphing now. I'm going to set up an XY axis, and I've got a y-intercept at 2. Let's indicate our scale here. So this is a 1 and 1, and then a y-intercept at 2. 2 over rad 3 is between 1 and 2, right? So there's going to be a point somewhere in there and a point somewhere in there on the positive and the negative side. I have a vertical asymptote at x equals 2, like so. And then I've got this slant asymptote, which has a y-intercept of 6. So there's 2, 4, 6 there. And then it's got a slope of 3. So I'm going to go 3, 1 right there. And let's try and go up 3 and over 1. So that's going like that. Okay. That's pretty narrow there, and then coming down this way. All right, so in this region here, right there, I'm pretty well set because I've already got some points, right? So I'm going to approach that asymptote and approach that asymptote. Remember, with rational functions, we think in vertical regions. So I'm thinking in this region because of the vertical asymptote at x equals 2. And then after thinking of that region, I'm going to look at this region over here because of that's to the right of x equals 2. So I'm just all I really want to do is find one point in here to figure out if the graph is in here or if it's up high here. So I'm going to do an additional point here, f of 1, 2, 3, f of 3. So look in the table over at the left. So I'm going to do f of 3. And let me see if I can do a quick calculation here. Okay, and I'm getting f of 3 is 23. So look there, that means that, so here, if you look at the graph now, if I take f of 3 and then way up at 23, I've got a point. So what that's really telling me is that my graph, I'm going to erase this writing here, my graph is going to fall into this area up here. So the graph is going to be up there. And I mean, my scale kind of threw me off here. So just to indicate, I'm just going to do this indication. Understand, it's not really to scale, but I'm going to have a piece of a graph up there. So definitely, if you're looking up there to the right, you can see what my idea is here. So the basic idea that I'm trying to show with this graph, just the general idea, and I do have some specific points and understanding this is not to scale up there, but the basic idea that I'm trying to talk about is that I've got a graph that has a vertical asymptote, it has a horizontal asymptote, and then the graph is falling in these narrower pieces of the pie, I guess you could say. And I'm showing that. You can see that in my graph there. So that's the graph of a rational function with a slant asymptote.